for more discussion of the previous papers, if anybody has more questions. There was some discussion with Denise on the chat channel. I don't know if anybody wants to discuss that in public.
Yeah, if possible, I would like to answer again Ravenda's question, because it seems that it was not clear.
Yeah, go ahead.
Okay. The point is that, yeah, it's true that very young planetary nebulae could have this O6 emission line as well, but this is very rare. In fact, you have like a handful of these guys. So I would worry really much more about the fact that at least at the mentalist of the galaxy, only 50–60% of the objectives show this emission. So even if we count all those we find in a certain galaxy, we need to assume that they will be like twice as much, because we will not never be able to observe in this way all the guys. So the contamination of the, for young planetary nebulae is not as important as other factors that we already know.
Any more general discussion or specific questions?
Denise had a question on the definition of the continuum filter. Because I see that the continuum is very wavy.
Yeah, it's true. And for that, well, I forgot. I can show you something here too. What is the here? Okay, so are you seeing this screen? Nice screen?
Yes, yeah.
Yes.
That's good.
Okay, so Martin, this is the definition of the filters we built. So you have the on band here, and to the left, the off band one, because as you see here in these examples, I mean, the continuum around this emission can be really messy, So you see guys like these and these, but continued with all the bands, all the, characteristics of the co-star. So this is why our off-band continues to the left, and they have like the full width at half maximum of both of them. It's similar in the two telescopes. And in addition of these, in order to avoid the false positives that you could have observing only on and off band in O6, you are adding the helium-2 and the H-alpha, because, if it's only a co-star that you get as a false positive here, this one will not show the helium-2 emission and, H-alpha as well. So this is the way you are trying to avoid this problem.
Okay, thank you, Denise. It seems reasonable.
Stop sharing. Yeah. I need to stop sharing this. Hello, how do you do? Are you still sharing the screen or not?
No, it's fine.
That's good.
Okay, thanks.
Any other questions for the speakers or any general discussion?
Elias, can you put again the peaks, the light curve of the gamma and optical that you have to see the time scale? Because yes. Okay, so the time scales are days.
Sorry. So time scales are days, yeah.
Yeah, so you think all these peaks that I see here, like this one, and this one, and this one, each one of them is kind of collision with a clamp or something?
Yes, so we are not sure why we exactly have these flares. It could be due to several things. So it could be that we have a clumpy ejecta. So the gas, the faster wind is meeting different densities or density inhomogeneities. It could be some kind of spiral structures forming early on during the rise to peak due to the binary motion, and the fast wind is sweeping through some spiral structures. Though like the early velocities could be a bit high to form tiny spirals. Yeah, these are like also some people using this nova exactly try to maybe consider the presence of multiple ejection or like shifting in the velocity of the wind that is leading to a change in the shock power. We are not sure, to be honest. But these are all speculations that we had in
Because
mind.
we see some peaks also in supernovae, and also people suggest ejection, but it might be something else, that you have an ejector going out slowly, even in novae, 5,000 kilometers per second, or I don't know what is a novae velocity, 1,000 kilometers per second?
Yeah, from few hundred to few thousand.
Okay, say 2,000. But then, because of the nova, you disturb the companion. And then the companion transfer mass to the white dwarf. As you have white dwarf here, companion, transfer mass for several days, and then you have jets. And the jets collide with the ejector to power little explosions here that give you all the activity. This is something I suggested for supernovae. So can you rule this out, or did anybody discuss this possibility?
I mean, there's some discussion that all these activities that we see are actually stuff happening on the white dwarf instead of due to some interaction between multiple flows. Yes, but do you have any solid evidence or counter evidence to rule out or confirm that? Not really.
Yeah. So it's still a possibility that the big serial activity on the white dwarf, including launching of jets.
Yes. As I said, some of the work in the literature suggests that some of the features that we see in the optical light curve, like these flares or other like multiple peaks, sometimes we see could be some stuff happening on the white dwarf, just like not due to interaction. But the fact that we see some new spectral features appearing sometimes with these features on the light curve, with new velocities that with absorptions coexisting, for example, with other spectral absorptions, that's why we suggest that there's a possibility of flows and interactions. I wish I had some slide from a different paper to show you what I'm talking about. But for example, if I go to, sorry, I need to go back to the beginning of my slides. Yeah. So here, for example, in some novae, instead of seeing just flares, we see multiple maxima that could last for like 30 days or 2 months, and then the nova fade again, and then they have another peak and fade again. And with every one of these peaks that last for months, sometimes we see gamma rays. And also in the spectra, we see new features with spectral components at greater velocities. This could be an optical depth effect and everything is happening on the white dwarf, or this could be due to interaction between flows of different velocities. So yeah, I really can't say.
I suggest both. I say the activity of the white dwarf launching the jets, the emission is from the collision of the jet. It's not the burning of the white dwarf.
Yeah, so. I mean, for me, I always get confused when we talk about jets. I prefer, like, I call them bipolar outflows, but people that call them jets, I'm happy with that.
Bipolar outflow jet, for me, it's the same, doesn't it?
Right.
Okay, good.
Thank you. Thanks.
I have a question for Noam. How do you make those marks on the slides?
Well, you see,
Magic. It's magic.
I have this pen, but this is red. The orange is this one. You have view option on the top. So if you push on the view option, you have annotate, and then I can draw here whatever I like. Usually I draw jets.
I don't seem to have that tool. Anyway, Valentin has a question.
Is it for me or should I just touch it?
Yes. Hello.
Valentin, did you have a question?
Yes. Can you hear me?
Yes.
It's a question to Jesus Toala.
Okay.
I hear.
Okay. Of course. Jesus, well, really very nice talk. I'm impressed by the dynamics of these nebular components you find. And have you estimated the mass at least for a molecular component?
Yes, I was discussing this with Carmen in the Slack. So the CO mass is something about 10 to the minus 5. And the other molecules is about 10 to the minus 8, something like that. So the dominant component is the CO.
So
Also, the dust
I mean,
is 10 to the minus 5.
the CO mass is the mass in carbon monoxide molecules.
Yes.
So when you take into account the relative abundance of CO, expected relative abundance, you would find a fraction of a solar mass as total mass of the expanding gas.
Yeah, but you cannot use the hydrogen to monoxide, carbon monoxide, the same as the usual, because these are very specific objects where you don't have any hydrogen. So this conversion factor, I'm not sure it could be applied to these hydrogen deficient ejecta. So in order to estimate the total mass, what we have done
So
for
maybe
other
the
objects
total.
is to
So maybe the total mass is not that high, but what would you think about the total mass? Maybe about 10 to the
I think
minus
so.
3
In
or
order
so?
to estimate it, yeah, something about that. So we've done this for Avril 30 and Avril 78. We'd use cloudy models in order to produce synthetic observations, which we can compare to optical, infrared, and so we estimated something about 10 to the minus 3. In those cases. The total mass of the hydrogen deficient ejecta accounting for dust and molecules and the ionized emission. Yeah, so you have to think that this VLTP occurs at the surface of the white Earth. So at the same time there's an explosion, but the star should be left without dramatic changes. Has to survive.
Very nice talk and very nice results. Congratulations.
Thanks.
Okay. I think we've just about reached the end of the session. Do the organizers have any remarks?
Well, I had not sure whether this is a question or a comment, but I was a bit puzzled by the fact that in the case of Novae, you have white dwarf, you have an accretion disk, and those are going to be able to produce collimated outflows. But in the case of born-again planetary nebulae, in the very late thermal pulse scenario, you don't expect or you don't need to have a binary companion. But in most of the cases, well, I would say in all the cases where we see a born-again event, Abel 58, 30, 78, HUBI1, we always see a collimated outflow and a disk. So I was wondering how such a violent event in a born-again explosion can produce this kind of collimated outflows. It really puzzled me.
Yeah, so with this ALMA data, if I can go, this is something that Daniel and I have been discussing because the abundances are as if you didn't have a companion. So the abundances is a VLTP single star evolution. And then you have this bipolar structure. So there must be something. So we came up with this idea about when the star experiences the VLTP, it must inflate the outer envelope, these layers, so that this should give room to this common envelope like evolution. And then this produces these bipolar ejections. This is the only so far scenario that I can think of in order to explain both the abundances and the bipolar and the jets, which such high velocities.
So why the companion in A30 did not shape? Because in Abel 30, We have spherical outer shell and inner bipolar.
Yeah, but the outer nebula is the classic planetary nebula produced by the, yeah, and it's also kind of like not completely round. It has some elliptical
In Abell
shape.
30,
Yeah, and also Abell 78. They're not like roundish or complete round. So
okay, so it's a
Okay,
single star. Yeah.
well, I mean, I don't know.
Well,
it has been
well,
suggested with.
Yeah, Abell 30 is a binary central star. It was recently detected by Jacob.
With Kepler. With Kepler.
So what is the orbital period there?
Was a
In
few
Abell
I
days.
don't remember.
Don't remember.
Yeah.
Need to check the paper.
So if it's a binary, so you have your answer, Martin. It's a
Mm.
binary star.
Yeah.
Nobody
Yeah.
here believed in single stars. I
Okay,
remember
guys,
in the first APN meeting, I think, Howard Bond, you mentioned about the binary. At that time, you were not convinced completely that all planetary nebulae are shaped by binary. You say, I find 15%, 1/5.
Oh, you convinced me years ago.
Yeah, no, but then at the first one in 94, you say something about dark. If it looked like a dark, and if dark, and so something.
Yeah, I have here Jacobi's paper. The period for
Okay.
the central star of Abell 30 is 1 day.
1 day. So 1 day is exactly the time you need to do the shaping. So everything is good. We have a binary companion. We can sleep well tonight.
Yeah. Okay. Now that we are relaxed on this topic, I would like to thank all the speakers for their talks in this session and in the session before. So unleash your microphones and clap to all people here. Thank you very much. We will resume the meeting tomorrow. Remember to keep an eye on the e-posters and PDFs that we have on the webpage, and also we'll make our best so we have tomorrow all the talks already on the web, on YouTube and on the webpage of the meeting. Have a
Thank
good
you.
time, guys. Bye bye.
Bye-bye.
Bye.
Bye bye. Bye bye.